with this first, let's say, warm-up for the day, I'm trying to catch up on what has been said about embedded security already yesterday. The main message is a small one, and I'll make sure to go back to that message at least for you to see it once. So the idea of today is to see how things come together in practice when we actually want to build, let's say, some embedded system with, of course, some security functionality realized by cryptography, and to see how we do things in practice. So for any basic system that we can think of, there's a minimal set of functional requirements, right? So that it's actually a meaningful system. Let's see if this works. Okay, so for example, we will want to have some minimal cryptographic functionality. As example, we could say, okay, probably we want to be able to encrypt or decrypt, okay, or maybe we want to be able to authenticate some data or verify authenticity of some data. You can replace this with any other functionality you want to think of. If you didn't know before, then for sure during the week you have learned that in order to do that, well, we need keys, right? So crypto needs keys, and these keys have to be stored somewhere, right? They're not just flying around in the air, but you want them to be in your device, and you also want them to be in your device after you rebooted your device, for example. So we'll need some form of non-volatile memory that will store the keys for us. In many deployments, we will actually want our device to be able to generate or to derive cryptographic keys. So we'll need some functionality for that. And we'll almost certainly need what he's going to talk about. We'll need random bits, okay? Because we need them everywhere. So you have seen lots of examples during the week. Random bits are really, really essential for many aspects of crypto. So we need them, for example, to generate keys. Many protocols require random bits for nonces and similar things. And later today, you will hear how we use random bits to protect implementations against attacks. Okay? So this is really just a very basic set of requirements. Some systems are even simpler, but many systems will be much more complex, and they will have more requirements, and they will build much, let's say, higher level functionality on top of this. But for the sake of rather giving you a comprehensive picture of a few things, that's the set of functionality that we pretty much focus on today. So these are the requirements, how we're going to build this. So of course, in order to be able to encrypt, decrypt, or authenticate, verify, we'll need some implementations of cryptographic algorithms. Hardware, software. Today we'll speak about both a little bit. Something that is essentially so important that I forgot to put it on the slide is that, of course, we want these implementations to be efficient. Okay? So it's easy to take a description of an algorithm and implement that in some way so that you compute the correct result. I mean, everybody can do that. The hard part is then to make it 100 times faster, 1,000 times faster, and so on. Okay? So whenever we speak about implementation, the word efficient is implicit there. We'll need some non-volatile memory to store the keys, or to store whatever other system parameters, IDs, and so on, stuff that we have to remember. We'll need key generation algorithms or key derivation algorithms, these sort of things. We'll speak today about an alternative for these 2 points, so for the NVM and for the implementations of key generation algorithms. We'll hear something about physical unclonable functions. And of course, we need a random number generator in the system because we need all these random bits. Okay? So, let's say that's the theory side of what we have to do today. And the practical side is that we actually have to do this for an embedded system. And as most of you have heard yesterday, embedded systems have a bit of special requirements. And we have to do this in a secure way. Okay? So, key point for the people who have not been here yesterday is that, in our view at least, embedded system security basically allows these two flashes, whatever you want to call them, that are not existent in the classical security model. Okay, so when we analyze cryptographic protocols, algorithms, and so on, we're only concerned with inputs and outputs of algorithms and whether an adversary can break the crypto using those. When we have embedded systems, it's often the case that the attacker can actually do much more powerful attacks by not attacking, let's say, the theoretical strength of the crypto, but rather by trying to somehow exploit weaknesses in the implementation. Yeah, so these can be devices, I don't know, maybe this is even encrypted while it's talking to that USB fob. There's lots of crypto running in phones and car keys, and these things, you have them in your hands, you can open them up, and you can do lots of things with them. Okay, so that's the key message. We speak about embedded security. It's not enough to take a secure cryptographic algorithm and implement that. Yeah? That's really the baseline. Yeah? But then you're not secure against many of the attacks you will see today. Yeah? But you have to make a secure implementation of a secure algorithm. We'll speak about that today. So we need secure implementations of cryptographic algorithms. Again, hardware, software, both is possible. For our mock-up system, we would need a form of secure non-volatile memory, not just any, but secure non-volatile memory. I'll show you in a second why. We would need secure implementations of key generation or derivation algorithms. But so many key derivation algorithms in particular are very similar to cryptographic algorithms, and it would be highly redundant to speak about both of that. So we decided not to do this, and we'll also not speak about NVM because that's a very, let's say, physical thing to do. We'll speak about puffs instead, but I will just explain you in 1 second why do we need secure non-volatile memory. And the question is, can you see the red and the blue dots? There are red and blue dots in this picture. Okay, here are some red dots. Okay, so this is EEPROM. This is E square prom. This is a old form of non-volatile memory. All right, and so the question is, if I cannot read out, let's say your keys are stored in this memory, and access to this memory is protected with a password, something like this. I don't know. Yeah, it's not possible to just read it out in the normal way. Are we done then? No. Because if I really want to know what's in your memory, I can essentially take that memory chip, open it up, until I polish it until I can see basically your transistors and your technology level. I put it under a microscope, or a scanning electron microscope in this case, and I get pictures like this. And if I understand how this memory works, and if I understand what I'm looking for, I can essentially, so first of all, this image just shows how the person found the relevant memory cells, and these two images here show basically that there is a threshold in the coloring of certain areas, and if you find this threshold, then you can divide. So here 0, 1, 0, 1, and then basically you can read out bits, for example key bits, just from imaging the memory. Okay, so this is not this is a publication, but this is known since, I don't know, I would say at least 10 years, maybe longer. So this is not rocket science. Of course, this is also not trivial to do. You need the right machinery and so on, but it's certainly possible. So storing keys just somewhere, should be okay. Depending on how valuable these keys are, just storing them may not be enough. Okay? But so today we'll not speak about that. But we will instead speak about physical unclonable functions, or secure physical unclonable functions, which in a way you can see as a replacement for secure key storage. You see later why. And then of course we will have the secure random number generator. That's essential. And with that, we essentially have already summarized the program of today, if you wish. So this is what it looks like if you take a chip, whatever chip. Normally you just see the black packaging that's around it. So that's this stuff here. If you open that up carefully, if you know what you're doing, then eventually you'll find somewhere inside a piece of silicon. And if you polish that nicely and if you make a very nice photograph of it, you get an image of this. I have no idea actually what this is, but just suppose this is the system that we're talking about today. So we'll speak about implementations of cryptography, implicit, efficient implementations of cryptography. We'll speak about random number generation. We'll speak about physical unclonable functions. And typically, a system will also have some software involved, right? So maybe even all the crypto is done entirely in hardware, but there's going to be some software that actually, does the I/O, calls the crypto, and so on, and handles all these things. And if that's not well protected, your attacker may actually try to go around your security by understanding what your software does and going around that. So we speak also today a little bit about software reverse engineering. This is my little picture here for the bad guys. So of course this system can be attacked not only by the crypto attacker who tries to break the cryptographic algorithms, but as most of you heard yesterday, we can actually do much more in terms of attacks, and that's how we're going to start today. But then fortunately we have on the good side also lots of ways how we can, let's say, strengthen implementations of algorithms, how can we protect them, how can we add countermeasures. We'll hear about that, a part of it, of course, only today as well. And then at the end of the day, we'll speak about so the last lecture is actually going to be about how should we build up a system when we know already from the beginning that it's going to be under attack later on. Okay, so when I made the slides, I was choosing between a picture of a prison or a picture of Fort Knox. Difference being, in the one case people want to get out, in the other case people want to get in. But the main point is the same. Yeah? This has not been just made to be a big building, so you can put many things inside. But it has been made a big building where you can put many things inside, and you want to make sure that nobody can come and take it outside. Right? So it has been already architected in a way to be secure against at least the attacks that were foreseen at that time. So that's security by design. Yeah? What happens often in practice is that people would actually just build, a large storage hall. Then other people would come and start to steal the gold, and then they would realize, oh, we have to put a big wall around it. That's then the patchwork things that we often deal with in practice. All right, so that's so far for the introduction part. So for the few people who were not here yesterday, we essentially said that yes, so cryptographic devices can be attacked not only in the theoretical mathematical way, but also in the physical way, and that we have a kind of classification of attacks, if you will, following whether the adversary is active or passive. in the sense of how he uses the device. Okay, I mean, he's always active, he does something. But if he uses the device in the way how it's supposed to be used, then we call him a passive attacker. If he actually manipulates the device, for example, opens it up or cuts out certain pieces and so on, then we call it an active attacker. And then depending on the degree of, let's say, how much he interferes with the device, we can call this a non-invasive attacker if essentially the device remains intact as it is. Okay, so if I just, for example, measure the temperature of my phone from here from a distance, that would be a non-invasive attacker. I don't open it, I don't do anything to it. Then we have on the other extreme end the fully invasive attacker, so he can open everything, he can destroy chips, he can rework chips and so on. And then since a couple of years we have this kind of new attacker who can even do things remote, because more and more embedded devices actually get online, they have whatever network connections, so that it's possible to exploit software bugs, especially through online interfaces. This first part today is about side channel attacks. Side channel attacks are passive attacks, so the device is only used in the normal way, in the intended way, and for the most part they are non-invasive attacks, meaning that we're just measuring some property of the device without interfering with it too much. Okay. So what's the key different thing to cryptanalysis that you have been hearing about so far? So we're not doing cryptanalysis, we're not doing black box security analysis, we're not doing mathematics. We're doing what we call gray box attacks, and it's more some physics, engineering type of thing. So we're not trying to break the mathematical strength of cryptographic algorithms, but we're trying to break the implementation. Okay, so this is the classical security model. We have this black box, there's a key inside, some algorithm is implemented here, some input goes in, some output goes out, and the attacker has input and output and tries to figure out mathematically what's the key. Okay, so if you choose any reasonable standardized cryptographic algorithm, you're most likely to fail in recovering the key. That's why we said, okay, let's try something else, because we don't like to fail. So there's this gray box model. Yeah? So in the physical world, for example, if we're looking at a smart card, the box is no longer black, but it's gray. It has some shade of gray. Okay, and it's supposed to symbolize that there's some additional information that we can learn from the implementation of the algorithm. Information that is not available here and here, but information that lives only during the execution of the algorithm. But if we can capture it, for example, with an oscilloscope, it will add a lot the breaking of the system. We will then not break the algorithm. Mathematically, it's still sound, but we will have broken that implementation of that algorithm. Okay, so that we can measure various physical quantities near the device that we want to analyze and use this extra information during the analysis. We'll give you lots of examples. If it's not clear now, don't worry. In 10 to 15 minutes, you'll say yes. Okay, so this is what we call side channel leakage this year. Yeah? So this additional information that somehow comes out and that will help us. Now, what sort of information could this be? It could be, for example, information about timing. How long does it take to perform a cryptographic operation? That would be, let's say, the overall execution time, or how long does it take to execute certain small parts of a cryptographic algorithm. You'll see examples later. Very popular is power analysis, and closely related is electromagnetic analysis. Here the key point is who's engineer? Few. Computer science? Mathematics? Okay. Who does not know what is CMOS? Don't be shy. Okay, so CMOS is basically 99.999% of all chips on this planet are built in a technology that's called CMOS. Okay, this is just the way how semiconductors work together and so on. The really cool thing about CMOS is that it only consumes power when it does something. Yeah? That's why we like it, because that's why your phone and your battery in your phone lasts maybe a couple of days, at least in the beginning when it's new. Okay? If you didn't have CMOS, it would be empty after 10 hours, because the phone would be consuming a lot of power all the time, even if it's sleeping. Okay? But so CMOS only consumes power when it does something. So that's nice for your battery. That's bad for your security, because this also means that by simply observing the power consumption, I can already figure out whether it's doing something, yes or no. Okay? So this seems not to be very interesting at first sight, but basically in the next 40 minutes I'll explain why this is very bad for security. And it affects, as I said, 99.999% of everything that we have on the planet. Yeah? So basic property, it consumes power when it does something, and it doesn't consume power when it doesn't do anything. And if you know how to use this property, you'll be able to break lots of things. If for whatever reason we're not able to measure the power consumption of a device, we may always be able to put some little antenna on top of the device, and some may know, some may not know, but so whenever there's an electric current flowing, that generates an electromagnetic field. So measuring the field is a little bit more difficult. It's not as convenient as measuring power, but whatever we can see in the field is going to be closely related to what we can see in the power consumption. People have shown many more exotic examples to be practical, in the sense that they actually carry information that can be exploited. Not as practical as the above, but at least it has been shown that it works. So people have even broken PGP running on laptops by listening to the sound that the power supply in the laptop makes. Okay, so if you have a certain brand of laptop with a certain type of motherboard with certain old capacitors that when they get high load they start to make some weird high frequency noises. If you know what you're doing, you can actually exploit this noise to figure out PGP keys in the laptop. And similar things you can do with light emitted by chips, temperature, and so on. So this magic thing, side channel leakage, well, it's first of all something that's not intended, right? So the person that implemented that system was hopefully not aware of this side channel leakage, because otherwise he would have put some countermeasures in place to protect against that. So it's something that at design time, when the system was built, implemented, and so on, people just didn't think about it. And of course, it's not supposed to be known, because as you will learn today, once it's known, it's easy to break that system, because it enables new kinds of attacks that wouldn't be possible without that extra information. And in a way, funny or sad, depending on the point of view, reality is that it's often optimizations that enable this information leakage. Yeah? So whenever you're trying to do something faster, for efficiency, whatever, this kind of thing can happen. So a very simple example at this point is a multiplier. Okay, so if you want to multiply two numbers in a microcontroller, for example, this takes a certain amount of time. There was a company, a very popular company that makes microcontrollers, that at some point in time thought, maybe we should first check if one of the operands is 0. And if we know that one of the operands is 0, we actually don't have to perform the multiplication, we just output 0 immediately. We can do this after one cycle, so we save 50% of the time. Yeah? Some years later, they made a secure version of that microcontroller that didn't have this feature anymore, because they figured out, or were told, that this actually leaks information about the operands. Yeah? So if you're not supposed to know that one operand is 0, just measuring the time, how long it takes to multiply, would tell you whether one of them is 0. So this is bad. Yeah, and as I told before, and as you maybe already also heard from the example, the device under attack is operated in normal conditions. So I just asked my multiplier to keep on multiplying these numbers. I didn't ask him to do anything strange. So it's extremely hard, maybe impossible, to detect these attacks. because you're not doing anything special. You're just observing additional information during normal execution. You're not doing anything strange. And this essentially means that countermeasures against this sort of attack, they have to be in place and active all the time, because you can't figure out when you're being attacked and when not. So to give another example, suppose that's a bank safe, that's the lock of a bank safe, and we want to open this thing, and that's really hard, because we have to dial in a very long combination of numbers correctly, right? So there's a huge space of possibilities, and guessing the right one is basically, it's not going to happen, right? So this is a very hard problem. And then what do we see in the movies? Well, in the movies we see, at least in the old movies, we would see some guy with a stethoscope, and he would start to listen to the lock, and he would start to listen to the clicks of the lock, and then suddenly, boop, and it would be open, right? And so why is that possible? Well, that's possible because basically the clicks tell him every time when he dialed one digit correct. Okay? So without that, you have to guess one long number correctly. With this, you have to guess, let's say, 10 numbers correctly. But for each number individually, you have here an acoustic side channel that tells you when the number has been guessed correctly. Okay? So here you have to guess 10 numbers correctly at once, and here you have to guess 10 times one number. Okay? So that's, at least for the computer scientists, for sure, divide and conquer is a very known concept. Okay? So whenever we can break the problem into small pieces, it becomes easy to solve, and that's basically what we do with many side channel attacks. Okay? Actually most cryptographic algorithms gain their cryptographic strength by repeating a weak function many times. Okay? And we do that because we want to understand the security of that function. Because it's difficult to understand the security of the function, we choose a weak function, so something simple that we can study very well, understand it very well, and then we just keep on repeating it, for example in rounds, until we believe, okay, now the overall construction is strong enough, assuming that the attacker can only see input and output. Okay? Other algorithms are not built like this. For example, most public key crypto is not built like this. But actually, when people implement them, they will fall back to the same structure. Okay? So modular exponentiation, for example, nobody will compute this in one step. This would be an enormously huge circuit. Yeah? But we'll break this huge complex computation into many small pieces and execute them one after the other. So that in the end, from an implementation perspective, again, the security builds up little by little by iterating something simpler many times. Yeah? And so the important observation is that the side channels, the various side channels, they leak information during this process. They leak information about the cryptographically not so strong intermediate results while the strength builds up. And of course, attackers, if they know what they're doing, they can gather this information and use this extra information to, in a way, yes, so to break this weak intermediate version of the algorithm during the processing, rather than the final result that should be hard. I will mainly use power analysis as example from now on, because that's really the most popular, and it's also, for me at least, the easiest to visualize and make pictures and put them on slides. And when we speak about measuring power consumption, we speak about something like this. So we call this a power trace or a power curve. Okay? So this is a vector of measurements over time. This is the time axis. This is an amplitude axis, so how much power is consumed. So we're not speaking about some average power consumption or peak power consumption or something, but we speak about something that is sampled continuously over time, a vector like this. Okay? To get that, we need some equipment in our lab. So here's the device that we want to attack, for example, a smart card. We need some probes, so something to measure whatever quantity we want to measure, power consumption, radiation, and so on. That will be connected to an oscilloscope. That's basically something that turns consumption into numbers so that we can use them later. We'll probably have to provide power, maybe some other signals to the device that we want to run, so that's all there. Then we need a computer to control everything and to orchestrate everything, because we don't want to sit in the lab for many years pushing buttons. Okay, and then with such a setup, we can start to do some analysis, get some data. So, as I said already before, CMOS is really the predominant technology. Everything is made from it. So if we open up a smart card, many people think that this golden stuff that you see, that's actually the chip. It's not. It's just contacts. The chip is much smaller. Yeah, it's only below the middle part of that golden contacts that your chip is. Okay, and then lots of it is just plastic to make it into this format that we like. And this little teeny tiny chip that's here, if you zoom on it, you get an image like that. So you see different regions, there's memories, there's logic, and so on. And this is built in CMOS. So CMOS has a relatively high power consumption, but most of the time our devices are not doing much. Right? All your phones, I hope, are now in your pockets. They're not doing anything, so they should not consume a lot of power. So as a consequence, somehow the power consumption of this logic depends on inputs, whether something happens or not. So don't be scared. This is the simplest logic circuit that we can build. It's an inverter. Okay? Output is not equal input. The simplest thing we have. So for example, if our input is at a high level, our output is going to be on a low level. And as our input goes to a low level, the output goes to a high level. Right? It's an inverter. That's what it does. In this table we see all the possible transitions that we can see on the input. So we can have a 0 on the input, and the input stays 0, so nothing happens. Output is high, stays high. We consume little power. That's what we want. Nothing happens, consume no power. Our input goes high, our output goes low, so we see some discharging event. Some power is going to go out of this device somehow. How is not so important. Input goes low, output goes high, we see a charging event. Okay, so we need to consume some power to make this happen here. Okay, we consume power. Input is high, stays high. Output is low, it stays low. Again, we don't consume much. Okay, so if I now cover this table and I just tell you which of these happened, there's a very high chance that just by observing the power consumption of this thing, you can actually tell me what was the input, what was the output. Right? This is the very, very basic principle. Now you have to zoom this up to a circuit that it contains 1 million of these or something like that, but the principle is this. Yeah? And even if I put 1 million other gates, logic gates, whatever, around it, this one guy is still got to be there. His information is maybe covered in lots of noise from all the other circuits that are doing something, but this guy is still there and he still does his little thing. So we just have to find it. Some practical things. So oscilloscopes can actually only measure voltages. They cannot measure currents or power consumption, this kind of thing. So in our little setup, we will need something that converts, let's say, for example, power consumption or supply currents into a voltage. Yeah, that's not very hard. So by simply inserting a resistor, for example, in the supply line, we can convert the current that goes through the resistor into some voltage across the resistor that we can measure. We can do that in the supply line or in the ground line. There's also things like current probes, for example, like this one here. They do this all for you, nicely integrated. There's lots of things to do. For electromagnetic field measurements, there's a large variety of probes, large ones, small ones, sensitive ones, not so sensitive ones, very sensitive ones, and so on. Okay? So there's a whole part of research that basically deals with how to get better measurements, how to acquire higher quality information, and so on. But so let's look at the more interesting stuff. Now when we have the measurement, what can we actually do with it? Okay? And what we typically see is that we see information, for example, in repetitive patterns. Yeah? These are usually coarse structures of an algorithm or of an implementation, for example, loops. We will see information in the time domain. So what happens when? Now, as I said with the multiplier, simply observing time can give us lots of information. What happens when, program flow, and so on. Amplitude, so how much power do we consume? Yeah? This can, in some cases, give us information about what exactly happens at a certain point in time, which may reveal things about data flow and so on. We'll see examples for that. Yeah? An important side information is that on a microcontroller, for example, yeah, if a microcontroller executes a certain instruction with different operand values, the power consumption will change, somehow in dependence on the operand values. Okay, so the total power consumption is going to be a sum of what's the operation and what's the operand. And if we keep the operation the same, but we change the operand, power consumption is going to go up and down. Now let's look at a couple of examples. And before we do that, I'm sure everybody except for the 3 people who are here for the first day today, everybody knows what's AES? Who does not know what's AES? Nigel again. Okay, Nigel. That's AES. That's all you need to know. 3, 4, 5, 6. Can you count? 7, 8, 9. Okay? That's all you need to know about AES. It has 4 basic building blocks. Somehow, in the middle, there are 9 rounds that are exact copies of each other. And in the end, there's something that is similar to a round, but it's a bit shorter because mixed columns is missing. Okay? So 9.75 rounds. That's all you need to know. Now we take a very simple smart card, 8-bit microcontroller. We ask somebody to implement AES in assembly and run it on that microcontroller, and we measure the power consumption. And we get a picture like this. So here we have time on the x-axis. On the y-axis we have how much power is consumed. And to make it a bit easier to spot, especially on the slide, we already inserted these red dotted lines. And you will easily see that it's trivial to find the rounds, right? So if I would tell you this is the power consumption of a cryptographic algorithm, which one is it? You would say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. That one's shorter. Must be AES 128. Yes, that's correct. Okay? So this is the kind of thing you can see. If we zoom in, for example, if we zoom, this is now only showing 2 rounds. We can also clearly see that it's not always the same, right? So this part of the measurement looks different from this part, looks different from this part. Yeah? But it repeats here. Okay? So this one seems to be similar to this one, so this is probably the same piece of code that is running again because it's a looped implementation, right? So there's some structure in this, right? So this helps us to understand what's happening where and so on. If we zoom in even further and we only look at a few clock cycles, so this is just power consumption of a few clock cycles. Okay? This doesn't give you now any immediate information, but what I want to show you is that essentially the height of these individual spikes, okay, so these are different clock cycles, different instructions being executed. And now if we would change the instruction or we would change the operand value, the spikes would be a little bit higher or lower, depending on that. Completely different example, RSA signature generation, you have heard about it. There's this little trick, Chinese remainder theorem, that makes it a lot faster. Okay? So if we implement, if somebody would say, can you please analyze this implementation of RSA signature generation? And if I see a measurement like this, then I know this implementation uses the CRT. Because there are 2 parts that are very similar that repeat. Okay, and then at the end there's the recombination stuff to compute the final signature. And then later on, somebody else will explain you what very nice fault attack you can run on such an implementation. So now we have seen that there is information in these measurements. Okay, but so how do we go from just having some information to an attack, right? So I showed you there are some patterns, but I mean, knowing the number of rounds, that's not so interesting, right? But so whenever it is actually possible to go from these patterns or the timing and so on to secret values, so if somehow these patterns or timing, whatever, depends on secret values, well, then we can actually start to build up an attack, right? There's lots of them. There's a whole field of research about it. They do nothing else. There's lots of names, lot of categories and so on. I'm not going to go into any details of that because anyway, not everybody agrees 100% which category which attack falls in. But so there's a whole zoo of stuff. That's the important point. The big words that you should hear is simple power analysis. We speak about that. I guess the collision attacks we'll skip if at all. I'll do them at the end. What you certainly have to hear about is DPA, so differential power analysis. The other stuff is on the slides. You'll have them later if you want to read them. There will be lots of time for that after the course. So, simple power analysis. First of all, I don't know why it's called simple, because it's not simple in the sense of easy to do, but it's simple to explain, fortunately. Yeah, but it's actually something really difficult that requires a lot of experience. So it basically just means to look at a measurement, what we already did. Yeah? You just put it on your screen, on a large screen, ideally, and you just look at this measurement with all your experience, with all your expertise, and you try to figure out what's going on. It's analysis of few measurements. From the attacker's point of view, in the worst case, you have only one. For example, if a device changes its key after every encryption, yeah, then I have only one measurement with the same key. Yeah, so I have one measurement, that's all I have, that's all I can use, and so on. Often it's going to be about exploitation of somehow direct key dependencies with the structure of the measurement. You'll see examples, don't worry. An interesting part is that we don't need to know input or output of the computation for the attack. But it's of course very convenient if we have input and output, because then we can actually verify if the key that we're guessing is the good one. Otherwise, we just say, oh, I think this is the key, but we cannot confirm that. Requires a lot of expertise, a lot of experience, very detailed knowledge about the target device and the implementation that we're looking at. All of these things help a lot. And we're going to look at examples, again, for patterns, for amplitude, and for timing. So for patterns, so relatively long patterns in measurements, if we're looking at symmetric crypto algorithms, we can, for example, find out what's the number of rounds of the algorithm. I showed you that example already. Yeah? If you don't know beforehand what algorithm you're actually analyzing, simply knowing the number of rounds can give you already a strong hint, right? If it's 9.75 or if it's 16, then you may have a good guess on which algorithm am I looking at. We may be able to see when memories are accessed, because that often consumes more power than anything else. If we're looking at asymmetric crypto algorithms, so for example RSA or ECC, if they are straightforwardly, I should say, implemented, not badly, but straightforwardly implemented, you'll be able to read off the key of a single measurement. We'll see that in a moment. If not, we'll certainly be able, for example, to figure out what's the key length. We might be able to see implementation details, like I showed you the example with the Chinese remainder theorem, that by simply looking at one measurement, we were able to say this must be an implementation with CRT. So, example, RSA signature generation. Okay, so we want to compute this. And our key here, our private exponent, is actually going to be represented as a bit string, an n-bit bit string. Okay. And as I said, any implementation or no implementation will compute this as a final, as a single huge operation, but it's going to be broken down. and the simplest way to do this is called square and multiply. Okay, so we're going to scan our private exponent bit by bit, starting from the most significant bit going to the least significant bit. Okay, and in every iteration of the loop, we will always perform a squaring operation on the input, and if the key bit is a 1, then we will in addition perform also a multiplication operation, and if it's not, then we won't. Okay, so there's this conditional operation depending on the value of the key bit, and that's going to be what breaks our neck. So I hope that you can see good enough despite the sun. So this is a measurement of some device that has a coprocessor for computing RSA signatures, and the coprocessor has been optimized for the squaring operation, in the sense that the squaring operation is the one that consumes less power. Said differently, the multiplication operation is the one that consumes more power. Okay, so we can look here and we see that there are parts that have this level of power consumption, and there are parts that have this level of power consumption. And from what I just told you, that little extra information about the processor tells you immediately, okay, so every time when I see this, that's a multiplication. Right? So, and we know that every loop iteration always has a squaring, and then some of them have a multiplication, namely those where the key bit is a 1. So we can basically take a ruler, we print this, we take a ruler, and then we chop this into pieces. We can start to write down 0 and 1 key bits on top of that, and then we have reconstructed our exponent. Well, you cannot see this, it's just the same thing in hex up there, not important. And there's the key. We can do something similar with EM radiation. So this is actually one of the first experiments that was done here in this research group. So this is a very fancy, not really fancy, copper wire loop antenna. Okay, this is an FPGA chip. You can't see it on this picture very good, but so it's an FPGA chip that implements some ECDSA or something like that, and that's a measurement of the EM radiation around the FPGA, and you can play a very similar game and essentially write down the bits of the secret scalar from a single measurement. It's the same thing. So that was my example for patterns. Amplitude. So if we can observe the amplitude of the power consumption in a certain clock cycle, in very, very extreme cases, you may be able to deduce immediately the exact value of operands. Okay, so this is of course devastating. Much more realistic is to say we may be able to deduce, for example, the Hamming weight of some operand. Already that can greatly reduce your search space if you know Hamming weights of a couple of, like if I tell you all the Hamming weights of the key bytes, it's going to be much easier to actually exhaust the remaining key space. If it's a software implementation, you may be able to figure out what kind of operation is executed in that clock cycle. That can be very useful for reverse engineering of implementation details, if you're trying to understand what's going on. People have been working on building disassemblers based on power consumption measurements. So here's a device, here's a power trace, tell me what code the device is running. Yeah? So this is, in extreme and simple cases, this is possible. Yeah, but it can certainly help you to understand a little bit what's going on. Can be very useful. So just to give an example, so this is again the power consumption measurement. Here's the time, here's the amplitude. And it's just a very simple code that does nothing, and then it just moves 1 byte of data from one place to a different place, and again it does nothing. So important point is, well, when it does nothing, repeat it. So there are about 10 measurements in this picture. Okay, they're all plotted on top of each other. Yeah? But here you see only one line, meaning that these 10 lines, they're actually lying on top of each other. Yeah? So the power consumption is always the same, because it's always doing the same thing. The instruction is just nop, nothing, do nothing. This is the only cycle where something happens, where we say take data from here and bring it over there. And we ask it to do that, but first we put here data with different Hamming weights. Okay, and now you see the different measurements plotted in the different colors, and they all represent data with different Hamming weights. Okay, so the message is here: the amplitude of the power consumption of a move instruction depends on how heavy the data is we're having to move. Okay, if I have to move all zeros, that consumes less power than I have to move all ones. Yeah? Doesn't sound so cool, but now suppose that somehow you have a magic oracle that, given this, returns Hamming weights. So you have some way to automatically translate this into Hamming weights of data. Okay? And now suppose that this is a measurement, for example, of the AS key schedule. Yeah? If I'm able to automatically, or by hand, whatever, but if I'm able to extract the Hamming weights not only of the AS master key, but of the AS master key and all the round keys, I have so much highly redundant information about the master key, that brute forcing this and figuring out what's actually the key is very simple, just from one measurement. If I'm able to extract all the Hamming weights of all the key bytes of all the round keys, I have a lot of redundant information. I need one plaintext ciphertext pair, because I need to guess a key, a possibly valid key, and then check whether it's correct. Okay, but so this is stuff we can do. Timing. So when does an operation happen? This can show data-dependent branches in software implementations, for example. So if a branch condition does not only depend directly on the key value, like in the RSA example, but if it also depends on the input. So if the branch is on some intermediate data, then I need to know the input as well in order to know what is the branch condition. So our classical example is AS mixed columns. Okay, AS mixed columns, everybody knows. It's basically this multiplication of a matrix with a vector, requires finite field multiplication, and a straightforward software implementation is going to use, or may use, branches as follows. So we want to perform this computation here. This vector equals this matrix times this vector. So we start, and the first thing we want to do is we want to multiply A0 by 2. Okay, and multiplication by 2 of the A0 in the AS field can be done by shifting the A0 one bit to the left. And if a carry occurs, then we need to XOR this with a constant, which is 1b in hex for the AS field. Okay, so if you want to do this in software, you would say, okay, I take my operand, I shift, then I check if I have a carry. If I have a carry, I do the XOR, right? So I implement it like my beginning of my AS now looks like this. I take my plaintext byte, I XOR that with my key byte, it goes to the S box. Now I have my A0, I perform my left shift. Do I have a carry? No. Cool, I'm done. Oh yes, I have a carry, so I need to do this extra information, extra operation, and then I'm done. Now if you take a measurement of a microcontroller doing this, there are two measurements here. One is black and one is red. Can you see that? You see the difference? Okay. So the important part is that one of the measurements has a very high spike here, and one of them has the very high spike here. Okay. And this spike is when the branching occurs. This branching. Go this way or go that way. Okay? So by knowing when this happens, we learned what is the MSB of this value, right? Because that's our branching condition. Okay, and so knowing the plaintext, I can now easily check which of the keys lead to an A0 where the MSB is either 1 or 0 based on what we have seen in the power trace. And that very quickly allows me then to again find the key. I'll skip this part. Giuseppe, how am I doing in time?
15 minutes.
Huh?
15.
15? That's okay. I'll do 5. Okay, so as I said, I'm going to skip the collision attacks because I really want that everybody hears differential power analysis. So differential power analysis is about analyzing not only one measurement but several, or most of the time many. And this essentially allows us to confirm or reject a hypothesis or a guess about some intermediate state of an implementation. Okay? So if this intermediate state depends on a key, which of course is the most interesting case for us, then this becomes an attack. Okay? And in order to do this, you basically need to be good at 3 disciplines, a little bit at least, cryptanalysis. So you need to understand how the algorithm works that you want to analyze. You need to understand what's a good intermediate value to target and what is not. There are differences. There's some engineering, of course, involved, because you need to be able to do all these measurements and so on, or you have a buddy or a colleague who does this for you. And you need to know a little bit something about statistics, because that's how we process the data. So I have 3 ways to explain it, and I run through these 3 ways. Some people prefer pictures, some people prefer equations, and so on. So I just do all the 3, and then hopefully one of them at least works for you. And if not, we can talk afterwards. So suppose, again, we want to look at AES without any particular protection. We have an input, a plaintext, and output, a ciphertext. That's the encryption of the plaintext under a certain key. The key sits in the smart card. Plaintext goes in, ciphertext comes out. And let's suppose, remember the example of the inverter, depending on the input bits, power consumption, yes or no. So suppose, for the example, this is actually quite true in practice, the processing of each bit affects the instantaneous power consumption of the device in similar way. Very simple. The bit is high power consumption. The bit is low power consumption. Okay, it's a simplification, but it's good enough. It works in practice. So now we have to choose a good intermediate result somewhere in the AES. What is important is that this result should depend only on few key bits, because we want to exhaust these key bits separately. Okay, so in the beginning of AES, we have the computation byte by byte, right? So we take a plaintext byte, we XOR it with a key byte. This goes to the S box, and so on. Yeah? So it's only at the end of the round, when mixed columns comes, that we start to mingle things together. So the beginning just looks like this, byte-wise. XOR, substitution box, and that's it. So, and that's going to be the point that we want to attack. So we have the output of the S box, and we'll just look at one bit of this output of the S box. Let's call this D. Okay. We take many power measurements when the chip processes varying whatever randomly chosen input data X. Okay. And now the fundamental idea is really key testing. Yeah. So we know the X. We don't know the K, but the K is only 1 byte. Okay, so we start. We say, okay, so if the key is 0, then the input of the S box is the same as the plaintext. Yeah? And then we're able to say, well, in this case, then the output of the S box has this certain value. We can just look it up. It's a table. And then we know what's the D. Okay, and so we can do this for each of the measurements with the respective input data. Yeah? So for each possible value of the key, from 0 to 255, we compute the value of the S box output. Yeah? And then eventually the value of our D, is it 0 or 1, for each of the measurements using the respective input data. And then we group our measurements into 2 sets. Now we have some measurements for which we determine the D should be a 0, and for the other ones the D should be a 1. Yeah? So we separate them in this way. Then we compute the average of all the measurements in that group and the average of all the measurements in that group, just to reduce a little bit the noise in the measurements. And then we compute the difference between these 2 averages. Okay? You get a differential curve. We call it differential curve. And the idea is that for the correct guess of the key, the differential curve will show some spikes. At that time index, when this selected bit, this D, that we were focusing on, when this is manipulated. Okay, that's the idea. And for all the other key guesses, this differential curve will be more or less flat. Yeah. Yeah, so I put it actually here so as a reminder for myself, but this time I did not forget it. So yes, the adversary does not know where in time, in which clock cycle is this intermediate value processed, so we have to analyze all of them. Yeah? And most of them, they will be completely meaningless, unrelated, they will not give us anything, but there will be a few points in the time domain that give us relevant information. So, to put this into picture, so we have measurements with associated plaintext. Okay, now we start. We take the first measurement and we say, let's assume the key is a 0. Yeah? Then my S-box output will be this value, and in this case the LSB is a 1. So I'm going to put you on the right side. All the guys with the 1, we put them on the right side. Okay? The next one, for the next plaintext, we determine the S-box output would be this value, the LSB is 0, so it stays here. Next one has a 1, goes there, and so on, yeah, for all of them. Then we compute the average. So this is the average of all the measurements on this side, and that's the average of all the measurements on that side. And then we subtract these two. Okay? And for this key 0, 0, we get a differential thing like this. Yeah? Now what? Are these spikes? I told you there should be spikes somewhere. Are these spikes? You can't tell. You can only tell when you have done this for all the keys, and then you compare them. Okay, so now we fast forward and we change the key. Now we're guessing that the key is 2b, and we get a differential thing that looks like this. That looks more like a spike, right? We're still not sure, but this looks more like a spike than the previous example. So show this in large. This could be maybe a differential trace for a wrong guess. Maybe this is one for a right guess. Just some examples, right? So it's hard to tell before you have computed them for all the key guesses. Now what we typically do is that we take the highest absolute value that we see in this entire thing. Okay, so for this key guess, I would probably use this value. And I would just remember this one value and say, this is the highest point I find for this key guess. Okay? And that is the highest point I find for this key guess. And now I make a new picture. This is not time anymore. These are the possible key values, 256 key values. Highest point I found for that key value. Okay? And then if you're lucky, if your attack works, there's going to be one that stands out and say, oh, it's me. Oh, guess me, guess me. Okay? So then you know your attack worked, and that key byte has that value. And now you repeat the whole story for all the other key bytes, and then you're done. So, third way to explain it for the people who like formulas, it's exactly the same thing. Okay? So, we have inputs, we have power consumption vectors, we have k prime, the targeted subkey. This fk prime xi is the chosen intermediate result, our S-box output, and the di is the LSB of that. Okay? So we have to compute these di's, ones or zeros. Yeah. So we multiply this with the power consumption vector, which means if my di, for example here, if my di is a 1, then this becomes a 0, so that just means that power trace does not contribute to this average, it contributes to this average. Yeah, so these are the two averages of the two groups, and we subtract them, and that's our differential trace for that guess. Same thing. Okay, and so it works. Why does it work? For the correct guess, our grouping actually makes sense. Yeah? We're putting the right traces in the right groups. And by assumption, we said that the value of each bit contributes to the power consumption. Right? So if we make this split properly and correct, yeah, then the two groups must have a significant difference by assumption. And then this kind of computation will reveal that. If the guess is wrong, then we're basically shuffling these measurements together in some random way. And there will be no meaningful significant difference between them. They will both, somehow contain 0.5 power consumption. So when we subtract them, nothing remains. That's why ideally this differential trace should be flat. 5 minutes? 2 minutes?
5 tops.
5? Tops. 2. I can do stop now. So just a few, let's say, more practical things. So the whole process is highly empirical and sampling based and so on. So one of the many things we have to deal with is noise. There's lots of noise. There's electrical noise in these measurements, yeah, because nothing is really, when it says this is 5 volt, it's not exactly 5 volts. It's something that fluctuates maybe very narrowly around 5 volts, but so we have electrical noise, we have quantization noise, so the oscilloscope that turns some power consumption into a number that I can process. This is quantization noise. This is not a perfect process. We have ambient noise, so if I repeat the same measurement at a different room temperature, the measurement will look different. All these sort of things. And the easiest way for us to compensate all these forms of noise is to increase the number of measurements. Yeah? The more measurements we can take, so if we increase the n in all the examples before, yeah, this will help us to reduce the noise. Because of this law of large numbers, the estimation of these averages, the noise in them will decrease in the square root of n. So if we make n larger, we get less noise. Here's an example. So if we throw a dice, so it can be 1, 2, 3, 4, 5, 6, the outcome, and we want to compute the average of this. Yeah, then we know if it's an ideal dice, every side shows up equally likely. We know that on average we should get 3.5, right? That's the average score of a dice. Now, if you do a random sampling experiment, and you simulate that the computer throws the dice, and you keep on computing the average, and this is the number of how many times do you repeat that. You see, once you do this often, I did 3 experiments, so blue, green, red. See, once you do this often enough, they all converge towards 3.5. But if you're here in this area, the results are quite unstable and they are quite different. That's just because you didn't use enough samples. So that means when we do DPA, and we are not sure, there's no clear peak that stands out. I mean, this is of course, this is the textbook example. Yeah, it's not often that it's that clear and say, hello, it's me. So when it's not like that, if no thingy is really obviously the right guess, we can always try to take more measurements and repeat the process, because maybe we were somewhere here and we didn't just use enough samples to get a clear result. So there's always the hope that if we increase the number of samples, we'll get a better result. Okay? So what I've said so far about DPA is I believe the easiest way to explain it. This is 20 years ago. Okay, so there's been lots of research on making this better somehow, improving things in various ways. It's on the slides. I will not speak about it because I think it's more important that everybody understands the basic thing than to follow up and see how are the improvements. That's not so hard, at least from my perspective. For me, when I started, the hardest part was to understand how is this magic possible. Yeah? Everything that follows afterwards is just about trying to make an attack work with less measurements, most of the time. Yeah. So how can I use the measurements that I already have in a more efficient way?
One question.
Yes.
There is some of the board that already have protection, like adding random noise on the chip. So does adding more measurement can help to find out the differential statistic, and we can break over the key based on that?
I didn't understand the last part.
My question is, if we add the measurement, can we recover the key, still recover the key, if the board already has protection by adding random noise
Yes.
on the chip?
So there's going to be some lecture about countermeasures, but essentially, if you increase the noise, so by really on the chip generating noise that influences the measurement, you're basically pushing the whole picture that way. Yeah? So you will force me to use more measurements. Yeah, it's like now I'm trying to talk to you, yeah, and there's a signal to noise ratio everybody in the room is quiet. If they all start talking, I will have to shout much more, right? So you have to make a better measurement, or I have to say it 20,000 times, and then you will have heard enough. Yeah, by adding noise, you just make it harder. The information is still there, it's just covered in lots of noise. So I'm going to stop here. All the other stuff is on the slides that you will get. The animations are a bit slow. And I just come to my last slide. So, what's important in practice? Measurement quality. Okay? So you can, if you don't have good measurements, you have a very hard time afterwards analyzing them. Yeah? Because they're noisy, or because they not even contain the right information, this sort of things. So we spend a fair amount of time on making sure that we have the best possible measurement to start with. Yeah? Because if you don't, everything afterwards becomes a lot more difficult. Synchronization is important, so we need to make sure that when we have many measurements, that they're synchronized, meaning that the same things happen at the same time indices. You know, if they are shifted against each other, we cannot do this statistical analysis straightforwardly. And we have to first somehow realign these measurements. There's a fair amount of automation, okay? Especially if you implement something that's protected or something that's a bit larger, you need a large amount of measurements. So we don't want to spend time in the lab, have machines to do this for us. And then most important is, of course, that reasonable devices will have countermeasures, and they hopefully make it much harder to break something. So, thanks for your attention.